In this lesson, we're going to choose functions to model data, write functions to model data, compare functions using average rates of change, and solve real-life problems involving different function types. So far, you have studied linear functions, exponential functions, and quadratic functions. You can use these functions to model data. So remember, here's a linear function. It is a line, and you can write it in the form of y equals mx plus b. Exponential functions, you can write in the form of y equals a times b to the power of x, and it looks like this. And then most recently, our quadratic functions, here standard form a x squared plus bx plus c, and we get our parabola here. For example 1, we're going to plot the points and tell whether the points appear to represent a linear, exponential, or quadratic function. So I'm going to zoom in on part A right now. So I have the point 4, 4, 2, 0, 0, 0, 1, negative 1/2, that'll be right around here, and then negative 2, 4. And if you see, this kind of looks like a parabola. So I'm going to draw a parabola through this, which means it's going to be a quadratic function. So here's my parabola. So now we're done with part A. Slide over for part B. 0, 1, which will be right here. 2, 4, 4, 7, negative 2, negative 2, and negative 4, negative 5. And if you see here, this is a linear relationship because I have a constant rate of change. So I'm going to write linear. Another way you could tell is because I could draw a line through these points, which is what I'm going to do right now. So now we're done with part B. Now I'm going to scroll over for part C. So I have 0, 2, 2, 8, 1, 4, negative 1, 1, negative 2, 1/2. And if you see, each time I'm increasing my x value by 1, I'm doubling my y value. So here I go from 1/2 to 1 to 2 to 4 to 8. So this is going to be an exponential relationship. So I'm going to sketch my curve here. Anyway, I've plotted these points and successfully identified all of these functions, and now we're done. Differences and ratios of functions. You can use patterns between consecutive data pairs to determine which type of function models the data. The differences of consecutive y values are called first differences. The differences of consecutive first differences are called second differences. So for a linear function, the first differences are always constant. For an exponential function, consecutive y values have a common ratio, which means we're multiplying the same thing each time. And then for a quadratic function, the second differences are constant. In all cases, the differences of consecutive x values need to be constant. In example 2, we're going to tell whether each table of values represents a linear, exponential, or quadratic function. And we're going to do that by finding the pattern. So I see for part A, for this table, each time I am increasing my x value by 1, because that's what's happening in my x row, I'm reducing my y value by 3. So if you notice, this is plus 1, plus 1, plus 1, plus 1, and then I'm subtracting 3 or adding negative 3 each time. So my first difference is a constant rate of change here. So this is going to be a linear function. Now I'm going to move over to part B. For this one, I'm adding 1 each time for x. But if you look at what's happening to y, I'm taking this one and I'm adding 1, but then I'm adding 2, but then I'm adding 4. So I'm not adding the same thing each time. Okay, but if you do notice, I am multiplying 2 each time. So this is times 2, times 2, times 2, and times 2. Okay, so I have a common ratio here, which means this has to be an exponential function. For every time I increase my x by 1, I'm multiplying by the same value to get to my next y value. So this is an exponential function. Anyway, let's move on to part C. So for this one, I'm adding 1 each time for x. So plus 1, plus 1, plus 1, plus 1. And let's see what I'm doing here. Well, I'm going from -1 to -2, so that's going to be -1. But then I'm going -2 to -1. That's going to be +1. And then from -1 to +2, that's +3. And then from 2 to 7, that's +5. Okay. Well, I know I'm not multiplying by the same number each time because -1 times 2 is -2. But if I multiply by 2 again, I would have gotten -4. So it's not going to be exponential. And I'm looking at my first differences here, and they're not constant. But I'm going to try to find my second differences. To get from -1 to 1, I'm adding 2. And then to get from 1 to 3, I'm also adding 2. And same with 3 to 5. So since my second differences, once again, second differences are the difference of your differences. Since my second differences are constant, this means it's going to be a quadratic function. Anyway, we've successfully identified all 3 of these tables as linear, exponential, and quadratic functions, and now we're done. For example 3, we're going to tell whether the table of values represents a linear, exponential, or quadratic function, and then we're going to write the function. So first I'm going to look at what's happening to my x, and I see that I'm adding 2 each time, so I'm going to write that down. And then over here, I'm going from 12 to 0. Well, I know it's not going to be exponential because if I was multiplying, I'd have to do 12 times 0, and then the rest of these would be 0. And that just wouldn't make sense. So now let's see if it's going to be linear. Well, here I'm getting from 12 to 0. Well, from 12 to 0, that's -12. And then 0 to 4, that's -4. And then -4 to 0, that's +4. And then 0 to 12, that's +12. Let's see if these second differences are consistent. Well, from -12 to -4, that's +8. And then from -4 to +4, that's also +8. And then 4 to 12, also +8. So I know it's going to be a quadratic function. Now to write this function, I can either use standard form, vertex form, or I could use intercepts. First, I'm going to show you how to do vertex form. So if you notice on this table, my vertex is going to be the ordered pair 6, -4, because 2 spaces away, my outputs are the same. Okay, so 2 spaces to the left, that's going to be a 0, and 2 spaces to the right of this point is going to be a 0. So my vertex is the point 6, -4. So all I would need to do is write my equation. So here's the general form of vertex form, y equals a times x minus h all squared plus k. So if I plug this in for h and k, I would get y equals a times, I'm going to scroll over here, and then x minus 6 all squared, and then minus 4. And all I need to do is plug in any non-vertex xy pair to solve for a. So I will choose 8, 0. Okay, any of these points besides 6, -4 would work as well. So if I plug in 8, 0, I'm going to get 0 equals a times, the x value is 8 minus 6 all squared minus 4. Okay, so first thing I'm going to do is simplify this. 8 minus 6 is 2, and then if I square 2, I get 4. So this would get 0 equals 4 times a minus 4. If I add 4 on both sides, I get 4 equals 4a, and then divide, I'm going to get a equals 1. If I plug this back in up here, I'm going to get y equals x minus 6 squared minus 4. So there is my function in vertex form. Now, if I wanted to use intercept form, I could as well, because if you look at this table right here, I have 2 zeros. Remember, a 0 is an x value that makes the output 0. So 4 makes the output 0, and 8 makes the output 0. So I could do the same thing, but instead of using my vertex, I would write y equals a times x minus 4 times a quantity x minus 8, because these are my 2 zeros. And then do the same thing, plug in a point that will help me solve for a. So I'm going to plug in the point 2, 12. So if I do 12 equals a, and then 2 minus 4 times 2 minus 8, I'm going to get -2 times -6 And then over here, I get 12. And this is going to turn into 12. So 12a equals 12. Once again, a is going to equal 1. So if I plug this in over here, I would get y equals just x minus 4 times x minus 8. Anyway, if you multiplied both of these functions out, our function that we got using intercept form and vertex form, they would be the exact same. If I FOILed this out down here, we'd get y equals x squared and then minus 4x and then minus 8x. That's going to give me minus 12x. And then plus 32. And then over here, if I did it this way, I would get y equals x squared minus 12x plus 36 minus 4. We're going to get the same thing. So writing the equation in any way that you want is going to work out. You're going to get the same answer either way if you use vertex or intercept form. Anyway, now we're done with this one. For nonlinear functions, the rate of change is not constant. You can compare two nonlinear functions over the same interval using their average rates of change. The average rate of change of a function, y equals f of x, between x equals a and x equals b, is the slope of the line through those 2 points, a comma f of a and b comma f of b. So if you look down here, the average rate of change is just the change in y over change in x, which you might recognize as slope. And for function notation, that's just going to be the output when x is equal to b minus the output of when x is equal to a over b minus a. It's the same thing. So here's what that would look like on a graph for an exponential function and a quadratic function. I'm going to scroll down here. Comparing functions using average rates of change. As a and b increase, the average rate of change between x equals a and x equals b of an increasing exponential function, y equals f of x, will eventually exceed the average rate of change between x equals a and x equals b of an increasing quadratic function, y equals g of x, or an increasing linear function, y equals h of x. So, as x increases, f of x will eventually exceed g of x or h of x. So all this is saying is, if you increase any linear function, any quadratic function, and any exponential function, after a while, the exponential function will always have the higher output value for a given input. As a and b increase, the average rate of change between x equals a and x equals b of an increasing quadratic function, y equals g of x, will eventually exceed the average rate of change between x equals a and x equals b of an increasing linear function, y equals h of x. So as x increases, g of x will eventually exceed h of x. So this one's saying that the quadratic function over time will pass the linear function over time once you make your input values really, really big. For this example, 2 social media websites open their memberships to the public. Part A, compare the websites by calculating and interpreting the average rates of change from day 10 to day 20. B, predict which website will have more members after 50 days. Explain. So first I'm going to do part A and figure out the average rate of change between these two websites. So I see from day 10 to day 20, for website A, I go from 1,400 members to 2,150. So what I'm going to do is 2,150 minus 1,400 over 20 minus 10. 2,150 minus 1,400 over 20 minus 10. Well, 2,150 minus 1,400 is going to be 750. And then over 10, that's going to be 75. So if we look at our rate of change, our output is members. So it's going to be number of members or new members per x for change in x, so per additional day. So it's going to be 75 members per day. On average. So that's for website A. For website B, I'm going to go look at the graph. I'm going to zoom in. So right here, I have my day 10, and then right here, I have day 20. So I'm going to call this about 1,800 and call this right about 900 because that's where this grid line is going to be. And these are just estimates because I don't have the exact points. So I'll do this over here. So that's going to be 1,800 minus, and then this will be, we'll call this about 900, over, and then once again, day 20 minus day 10. So this is going to be 900 over 10, which simplifies to about 90 members per day on average. So now we're done with part A. Let's go back to part B. Part B says to predict which website will have more members after 50 days. Well, after 20 days, we know that website A has 2150, which is more than website B, which is 1800. But if you look at the relationship here, as I add the same amount of days, so I'm adding 5 days in my X column, I'm adding the same number of members in my Y column. I'm adding 375. So from here to here, that's plus 375, plus 375, plus 375, and so on. Now over here, I can tell this is not a linear function because it's not a line, it's a curve. And it looks like website B is probably a quadratic function just based on the type of curve. This seems like part of a parabola. Anyway, we know that quadratic functions over time grow faster than linear functions. And at 25 days, this is at 25, 25. At 25 days here, this is at about the same. This should be at about 24, maybe a little bit lower. But if we added 25 more days to this, this growth rate is going to be much higher than the linear growth rate. So my prediction is that website B is going to have more members, assuming that this trajectory continues. So for part B, I'll write that down here. Website B will have more members as it is growing faster than the linear function in website A. Anyway, now we're done with this one. So for example 5, we have, in 1900, Littleton had a population of 1,000 people. Littleton's population increased by 50 people each year. In 1900, Tinyville had a population of 500 people. Tinyville's population increased by 5% each year. So in part A, it asks, in what year were the populations about equal? Well, what we're going to need to do is write two functions and then set them equal to each other. So I have in Littleton, I'm going to have a linear function because I start with my value, 1,000 people, and then I'm adding the same amount of people each year. So if I have Y is the number of people, and X is the number of years after 1900, I know that my y-intercept is going to be 1,000 because that's how many I start with in 1900. And then each year I add 50, so that's going to be my slope. So this will be y equals 50x plus 1,000. So notice that this is going to be a linear function. Now for Tinyville, I have a starting population of 500 people, but the population increases by percent each year. So this is telling me that it's going to be an exponential function. Remember, a 5% increase is the same thing as multiplying something by 1.05. So this is going to look like y equals my starting value, 500, and then times 1.05, which represents the 5% increase. And since it's each year, I'm going to do to the power of x, because that's the number of years here. So anyway, I'm going to compare these functions. Well, the only way we know how to solve a function like this so far is by graphing it. So I'm going to put these on a graphing calculator. So I'm going to graph y equals 50x plus 1,000, and then y equals 500 times 1.05 to the power of x. So now I can't see these, so I'm going to need to scroll out a bit. And I see that these actually intersect in the negatives, which means nothing to us because that would mean we need to go back in time. But let's see if they go intersect a bit more. I'm going to make my x range a little bit smaller and scroll up. All right, here we go. So if I just click right here, I can see where they intersect. So it's 34.9 blah, 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 which is very close to year 35. So if I go back here, for part A, it asks, in what year were the populations about equal? So that's going to be 1935. Because that's 35 years after 1900. Now I'm going to look at part B. For part B, suppose Littleton's initial population doubled to 2,000 and maintained a constant rate of increase of 50 people each year. Did Tinyville's population still catch up to Littleton's population? If so, what year? So instead of starting with 1,000 people here, they're going to start with 2,000. So I'm going to rewrite this for part B. y equals 50x plus 2,000. I'm going to change that on Desmos right now. So I'm just going to blank this one out, and I'm going to rewrite this as y equals 50x plus 2,000. And now let's see where they intersect. Right here. So that is 43.49 whatever. So that means, if I go back here, that sometime in 1943, about halfway through 1943, the populations would catch up if they started with 2,000 people instead of 1,000 people. So anyway, now we're done with part B. Now let's take a look at part C. Suppose Littleton's rate of increase doubled to 100 people each year, in addition to doubling the initial population. Did Tinyville's population still catch up to Littleton's population? Explain. So the answer is going to be yes, because we're dealing with a linear function versus an exponential function, and as we increase our x values, the exponential function will always end up surpassing the linear function. But I'm just going to write that out. So if we look back here, we had 50x plus 1,000. Now I've doubled my initial population to 2,000, so plus 50x. But for this scenario, we're going to have 100 people joining each year instead of 50. So it's going to be 100x plus 2,000. And then I want to see where that intersects with this graph. So if I go back here, I'm going to blank the red one out. I'm going to have y equals 100x plus 2,000. And let's see. So if I go back up here, that's going to be right there. So x is 55.629, blah, 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 whatever. So that means somewhere in between 1955 and 1956, we know that the population of Tinyville is going to catch up. And once again, that's because we have the exponential growth rather than the linear growth. So if I go back here and look back at what the question asks, it says, did Tinyville's population still catch up? Yes, because Tinyville has an exponential relationship that will always beat out, I'm going to use that in quotes because that might not be the exact math term, but it would always beat out the linear relationship. Anyway, we finished parts A, B, and C, and now we're done.